One bam. We're going to start off today by first closing off. This is a question you looked at last time, right? Was that Wednesday? No, Tuesday afternoon. Okay, this is one of the questions you some of you had trouble looking at, and then we'll have a look at a couple more different kinds of cases, still under the heading of rational polynomials. Okay. So we've learnt so far. I'm just looking at this and trying to rephrase it, right? We're going to head toward integration. But just so I don't have to write integral dx many times before I actually get to the integration, I'm just going to leave it like that. Okay. Now, can someone tell me, why is it that our normal strategy for dividing this up into partial fractions, why is it that our normal strategy fails? Why is it that our normal strategy fails? Now, just before I show you why it fails, that wording is important. I hope you get that. I don't know, when I was going through year 11, classic example, you know in 3 unit, right? What kinds of things do you learn under, say, the heading of trig? You learn how to solve equations, then you learn auxiliary angle, then you learn general solution, then you learn T method, and a lot of them, they really overlap, don't they? And I distinctly remember thinking to myself, why are we learning so many ways of doing the same thing? Like, is it just because they want to make life hard? The answer is no. It's because those strategies, they sometimes fail, so you use different alternatives, right? And this is exactly what's happening here, okay? What's this denominator? It's x minus 2 times x minus 2. So if you were to break it up into one fraction over here for one factor and another one over here, you would end up with this. Right? Those are the two factors, right? But because it's a double factor, it doesn't work. Why not? What's the problem? Keeping in mind that A and B, they're just real numbers. Good morning. The reason it breaks down is, or maybe I should say, the reason why partial fractions usually works is when you put these two together, right, you have to get a common denominator. You end back where you started, right? But you don't need to do anything like that when you put these on a common denominator because they already have a common denominator. X minus 2. This one's linear, but this one's quadratic. So you're stuck, okay? So the question is, how can we do something still with this to form partial fractions, okay? What must one of these denominators be in order to end up with an x minus 2 all squared, right? And the answer is, one of them has to be an x minus 2 all squared, okay? Now, some of you may not have written it like this, and you still would have gotten the same expression at the end, but this is the way that I'm going to advise that you actually follow through, because it means you start off in much the same way, and basically you can proceed as usual. So watch, okay? On the right-hand side, I'm going to put everything together, okay? Now, to do that, I need the common denominator over here. So I might do this in another color so you can see what's going on. If I want this as a common denominator, right, I'll have to multiply by x minus 2 over here. So I do it to the top as well. Now you can see my numerators I can compare, right? So, good morning. So I've got this. Okay, now at this point, we're in a good position, right? Because there's a trick we can take advantage of that will, even though we've got so many unknowns, we can work out what some of them are, right? What might you suggest? Think about the way you normally do partial fractions. Yeah, let's try out when x equals 2, right? Because that's going to eliminate this part over here, right? So by now you've done this a few times, you're going to see what's going to happen. You probably don't need to put in every line of working. Over here, what are you going to get? 8 minus 7, which is 1. Over here, this x minus 2 will vanish. So you just get 8, right? Cool, good. I've got one value. From here, there are two ways to get the other value, okay? Any suggestions? Okay, so the first way I could do it, let's go over here, is I could equate coefficients. I just have to take this value, right? Stick it in here, but I need to expand everything out. Okay, so let's do that. I'll get 4x minus 7 equals 1 plus bx minus 2b. Okay, so you look, we're after coefficients here, right? I don't really need to worry about these guys because they're the constants, right? What I'm really interested in is these. That makes the easiest comparison, the most straightforward one. There are 4 x's over here and b over here. They have to be the same. There's nowhere else for the x's to come from, right? So just like in auxiliary angle, you can say, well, b must equal 4 by comparison of coefficients. Don't write that, I'm just in a hurry. You see what's going on, okay? Yeah. Now, by the way, I said that's not the only way to do it. Is there any, what could you suggest? Okay, I can actually put a value in, right? Which, by the way, is sort of like if you did have a factor here, which we usually do, right? That's getting rid of that value over there, right? So I would say, instead of when x equals 2, 0 is just the easiest number I can put in, right? So when x equals 0, what do I get on the left-hand side? Just -7. I already know what a is, and then I've got -2 lots of b, right? So just tidying that up, -2b, -8, and no surprises there, okay? So now you can rewrite your original rational polynomial in terms of partial fractions. Do you need me to integrate it, or do you think you can handle it from there? I think you could do it. Just watch out for this term here. Right? Because you're used to things like this turning into logs, right? But this does not turn into a log because it's squared, right? If you have trouble with working out what that is, just let me know and I'll show you, okay?